All right, welcome back. We'll do some more examples with local max with optimization using a max-min process. We're going back to a fence question. This time, it's horses being protected, and that changes everything. No, it doesn't. What actually changes everything is that this farmer is building the fence along a river. The horses have nothing to do with it. So I'm going to draw a river. Then I'm going to draw the fencing. Actually, I don't want to... Yeah, never mind. I'll draw the river blue. That's fine. Now I'll draw the fence. Better draw the fence red like the last one. Now I don't want to do this with an experiment. Because maybe it's a fractional answer. Maybe it's like 33.333, right? I take 100 divided by 3. Do I have to guess that? Or maybe it's not 33.333. Maybe the other side, the right-hand side, is 46.7 or 52.8 or something. Like, how do I know I'm going to guess the right thing? I don't want to use guessing. I want to use a mechanical process, so I'm going to do the exact same strategy as in the previous example. I'm going to build a fence along the river. I'm only using 3 sides, so I'm going to label X and X, 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 and then one single Y. I don't have a Y on the left-hand side. I'm using the river as like a free fence. And it's worth writing that down. Like, this is not magic. There is a free resource here. It's like we have extra fencing. River is like free fencing. Philosophically, we can think of it this way. The river, that side, if we're thinking about it as a fence, we can either use a little bit of that free resource and draw a fence like this. So we're just borrowing a tiny, tiny bit of the river. We're using a tiny bit of that free resource, or we can use a lot of it. We can use like a huge amount and draw a fence like that. Balanced against the fact that the closer to a square we get, or actually the closer to a circle we get, the more efficient our construction of an area is going to be for a given perimeter. So we're balancing these two competing effects. We have a free resource, and we want to keep something as close to a square as we can. And they're fighting each other, like they're arguing over which one is the dominant force, which one has the dominant effect. We don't need to concern ourselves with this philosophy of the problem. We can just attack it using calculus. We can attack it by creating a function that represents the area. So the area function A is equal to length times width is equal to x times y, just like before. And our perimeter is equal to 100. And our perimeter is 2x plus y is equal to 100. It used to be 2x plus 2y is equal to 100. Now it's just 2x plus 1y is equal to 100. And that changes everything. Let's rearrange, isolate for y. Y is equal to 100 minus 2x. I'm going to take this expression. We're going to plug it in for y over here. So A is equal to x times 100 minus 2x. So A is equal to 100x minus 2x squared. Now we do calculus on this function. So we're going to take the derivative with respect to x. A prime is equal to 100 minus 4x. We're looking for critical numbers, so we're going to set the derivative to 0. 0 is equal to 100 minus 4x. We're going to add 4x to both sides. 4x is equal to 100. So x is 100 divided by 4, which is 25. But is this a max or is it a min? We always need to check this. Because when you do optimization, this process does not distinguish between max and min up until this point. This is just a critical number. This could be the worst. So what I'll do is I'll take the derivative again. A prime is equal to 100 minus 4x. A double prime is equal to 0 minus 4, which is negative. For all x, that means a of x, our area function, is concave down. That means x equals 25 is a max. And make sure I wrote that down correctly on the last slide. Max, okay. So that's by the combo test. Next, now what do? Well, we can state our solution. Thus, x is equal to 25 and y is equal to 100 minus 2 times x, so 2 times 25, which is 50. And our maximum area is going to be double what the previous one was. The previous one, we got 25 times 25, 625. This one will be twice that because it's 25 times 50. So by adding in that extra side, by adding in that free resource, that free river, we've doubled how much area can be enclosed, which is kind of amazing. And we can be 100% certain that this is the maximum area. Let's look at another type. This is again a fence question, but it's multiple pieces or multiple regions of fence. This farmer has 140 meters of fencing and wants to create 6 equal-sized stalls against a barn. So just like in the last example where the river was being used as a free resource, the farmer is using the barn as a free resource. So building just the fencing along one side and then dividing it up into different regions. So we want to decide the dimensions of the stalls that will maximize the total area enclosed by the stalls. I'm going to look at the labeling this in a particular way. Sometimes you might be tempted to call this entire thing y, but think about what the question is asking us to do. It wants the total, to maximize the total area enclosed by the stalls. We could do that. We could say the entire thing is y, or we could just say this thing is y. That means this is also y, and this is y, and this is y, and this is y, and this is y. And then each of these we could call them x, 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 and an x. Let's think about the perimeter part. Our total perimeter is our total fencing, again, which is 140 this time. Now, how many pieces do we have? How many x pieces? We have 1, 2, 3, 4, 5, 6, 7. So 7x, and how many y? 1, 2, 3, 4, 5, 6, plus 6y is equal to 140. All right. Now our total area is not x times y. It's 6 multiplied by length times width, because we have 6 of them. Equals 6xy. Now if we call the entire thing going up and down y, then your area would just be x times y. And you can try that approach if you want. We will end up with the same answer at the end. Okay, now what did we do in the last example? Once we got to an area expression with 2 variables, we looked at our perimeter expression, the expression that relates x to y, and we rearranged it to get y all by itself. So we'll do that here. So I'm going to subtract 7x from both sides. So 6y is equal to 140 minus 7x, and then divide both sides by 6. 140 minus 7x all divided by 6. You can divide each piece by 6 if you want, but I'm thinking ahead. I'm thinking of this as like chess. A little bit like chess. At least think one move ahead. If I take this expression for y and substitute it over on the left-hand side, I have a 6 on top and a 6 on the bottom. Those are going to cancel. So all that work of dividing up the fractions is just extra fuss. It's not going to matter. It's all going to cancel out. Okay, so is equal to 6x times that expression that was just there for y. 140 minus 7x all over 6. The 6 cancels top and bottom. And we get our area function a of x is equal to 140x minus 7x squared. Now we'll do calculus. So everything up to this point has not been calculus. It's been problem solving. So a prime is equal to 140 minus 14x. We're looking for critical numbers, so we set the derivative to 0. 140 minus 14x. I'm going to add 14x to both sides, and then divide both sides by 14, so we get x is equal to 10. Is it a max or is it a min? So we found that a prime of x was 140 minus 14x. A double prime of x is 0 minus 14, which is negative. So it's concave down for all x. That means it's concave down at our critical point, just like the last examples. Thus, max at x equals 10. So our solution is max area if x equals 10 and then y is equal to 140 minus 70 all over 6. 70 divided by 6, which is 35 over 3. So that would be the mix that would cause the maximum area. If you use x is 10, y is 35 divided by 3. I'm just paranoid that I didn't divide properly, but it looks like it's okay. All right, what if the farmer has a different configuration? What if it's like this? It's too deep. So it's instead of 6 stalls of equal size, it's 12 stalls of equal size. Now what do you do? And there's like different problems in this one too. You could imagine getting rid of, let's say this, getting rid of this piece, get rid of that piece of fence, and then get rid of this piece of fence, and get rid of this piece of fence. And what would you do? You just have to be very careful how you label things. Which things are X, which things are Y, and just adding things up properly. So it doesn't matter what it looks like. You solve all problems like this in the same way. I've already added labels for what I'm going to call X, what I'm going to call Y. I just have to, I'm going to erase them because I don't want them, I want them in purple. So sorry to myself, I'm putting them in purple. So X. We're again using that barn as a free resource. You got Y there, and you gotta be careful. We also have Y here. Don't want to miss those. Now what's our perimeter? Is equal to 120. So that's all of our fencing. We're going to use it all again. How many x's do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14x plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, forgot a y. 11, 12. Plus 12y is equal to 120. Now what's our area? A of x is equal to, not x times y. X times y is one of them. We have 12 of those things. So 12 xy We have 12 parcels, 12 fenced-in regions. And then we're going to do the exact same thing we did in the last example. We need to rearrange this expression in the perimeter to get y all by itself. So I'm going to subtract 14x from both sides. 12y is equal to 120 minus 14x. And then divide both sides by 12. Y is equal to 120 minus 14x, all divided by 12. I'm going to take that and plug it into the bracket for y. 120 minus 14x all over 12. We're going to get the 12s to cancel again. We're going to get the constants to cancel. And we get a nice area function. A of x is equal to 120x minus 14x squared. Now what? Same as before, now we do calculus. Okay, so we're going to take the derivative, set it equal to 0. 120 minus 28x. 0 is equal to 120 minus 28x. So 28x is equal to 120, adding 28x to both sides. Now divide both sides by 28. 120 divided by 28. Which is 60 divided by 14. And we can divide again by 2 if you want. So 30 divided by 7, doesn't matter. Is it a max? A double prime is equal to 0 minus 28, which is negative. So max, so I should write down the usual concave down. For all x. So max at x equals 60 over 14. We're not done yet. Y is equal to 120 minus 14 times x, so 14 times 60 over 14, all divided by 12. So 120 minus 60 all over 12, 60 divided by 12, which is 5. So that's our answer. The maximized area will occur at these dimensions. X is 60 divided by 14, y is 5. Okay, similar example. Doesn't look similar, but it actually is. This problem says that we have two numbers, x and y, that sum to 100, and we want to maximize the function x squared times y. So we have x plus y is equal to 100. Maximize f equals x squared y. I just gave it a name. I called it f because it says function. You can call it a if you want for area, or b if you want for b. Anything, doesn't matter. We want this to be one variable. So I'm going to do the same thing we did with the fence problem. I'm going to get y all by itself. Y is equal to 100 minus x, and substitute it in. So the function f is equal to x squared times 100 minus x. So f is equal to 100x squared minus x cubed. Now we're going to do calculus. We have a function. Do calculus. Okay, so we take the derivative. F prime is equal to 200x minus 3x squared. Now, I didn't pick very nice numbers, did I? That's okay. Next step, we have to factor. I'm going to factor an x out. Yes, we can factor more out if you want to create fractions, but I don't want to create fractions. We're setting the derivative to 0 and we're factoring x out, so we have 200 minus 3x. We have two solutions. This didn't happen in the fence question. So the structure at the beginning was very similar. We had an expression we're looking to maximize. It had two variables in it. We then used one other piece of information from the question to rewrite that expression in terms of one variable. We took the derivative, we set it to 0. Previously, we only found one critical number. Now we find two. We find either x is 0 or 200 minus 3x is 0. And that one means 3x is equal to 200, which means x is equal to 200 divided by 3. We can either make a number line and check for increasing and decreasing, or we can do the second derivative test. We can do the combo test. So I'm going to do the combo test. Do combo test. I'm going to find the second derivative. F double prime is equal to 200 minus 6x. Now we're going to evaluate this second derivative at both critical numbers. F double prime at 0 and F double prime at 200 over 3. So 200 minus 0, which is positive. So that's concave up. And that means there's a max, or sorry, that means there's a min. Min at x equals 0. For the other one, f double prime of 200 over 3, we have 200 minus 6 times 200 over 3. So that's going to be negative 200, which is negative. That's concave down at x equals 200 over 3. That means there is a max at 200 over 3. And then y is equal to 100 minus that. So 300 over 3 minus 200 over 3 is 100 over 3. So that's our solution. That's where the maximum value occurs for a problem like this. And let's do one more inside the same video. I know we're past the 20-minute mark, but these are all kind of themed together. I don't want to break them up. Well, this time we have a product of two numbers is 100. So I write that down. X times y is equal to 100. And we want to max the function f equals 32x plus 2y. How do we do this? Well, we're going to do the same process. Even though it looks very different, I want this function we're looking to maximize to be a function of one variable. So I'm going to rearrange this expression, x times y is equal to 100, to get y all by itself. Y is equal to 100 divided by x, divide both sides by x. Now I'm going to substitute it in. So f is equal to 32x plus 2 times 100 over x. So f is equal to 32x plus 200x to the power of negative 1, using the laws of exponents. Now we'll take the derivative. We're going to do calculus. So f prime is 32 minus 200x to the power of negative 2. We're going to set the first derivative to 0. Minus 200 over x squared. So 200 over x squared is equal to 32. Then I'm going to square root, or I'm going to cross multiply. So 200 is equal to 32x squared. Then divide both sides by 32. So x squared is equal to 200 divided by 32. I'm going to divide top and bottom, let's see, by 2. Let's just do 2. So 100 over 16. And let's divide top and bottom by 4 now, which is 25 over 4. So if x squared is equal to 25 over 4, we take the square root of both sides. We get x is equal to 5 over 2 and x is equal to negative 5 over 2. Since both of those quantities squared gives you 25 over 4. So again, just taking the square root of both sides. Next, we have to check, is it concave up or is it concave down? Which is a max and which is a min? Max or min? So we're going to take the second derivative, f double prime. Derivative of 32 is 0. And then the next one we get plus 400 x to the power of negative 3, which is 400 divided by x cubed. Now we're going to check the concavity. This is combo test. So f double prime at 5 over 2 is equal to 400 divided by 5 over 2 cubed, which is a positive number. So that's concave up. So it's a min at x equals 5 over 2. Now we'll check for the max, or I gave it away. We'll check the other point, f double prime at negative 5 over 2. Hold on a second. This is a trick. Hold on. This is a trick. We're looking to maximize the function. So we found critical numbers. Now we go back to the previous function here. This function did not have any denominator x values. This is a polynomial type function. This function has a denominator of x. When we bring it down to one variable, there's an x in the bottom. This function is not continuous. This function has a vertical asymptote at x equals 0. And what's happening here is that this function has no max. So we will find there is a local max at x equals negative 5 over 2 and local min at x equals positive 5 over 2. So that's from checking the concavity, the thing that I just erased, but no global max and no global min. I'll show you why. I'll show you why this question was not, I didn't construct it properly, and I think it's a good thing. I'll show you what is meant by this. All right, so I've pulled up a Desmos window. I'm going to graph the function that's obtained after we got it to be one variable. So 32x plus 200 over x. All right, I'm going to zoom out. Oh, my axes are chosen poorly. Hold on. This is just automatically generated axes. I'm going to go from negative 10, I guess. Negative 10 to 10. That's better. All right, and this is why there's no max and why there's no min. No global max, no global min. I can make this output of this function f as negative as I want by taking a number, an x value, that's to the left of 0. So like negative 0.0001, I'll get a very small output here. Very negative output. But if I take a number that's close to 0 and positive, like positive 0.0001, I'm going to get a very, very large value. So what's happening is that we're not getting a global max and global min because this function is not continuous. It has a discontinuity at 0. So this is not a good question. Not a good question. Not a well-constructed question. It is, however, a well-constructed question to show that just because you have a recipe for finding max and min, like if you were to plug this into a computer algorithm to find the max and min, it will spit out those two x values. And that does not mean it has found the max and has found the min. Quite the opposite. It's found only local max and local min. It's found those values. So it's found that value there. Where's my screen? This value here, 2.5, so 5 over 2. The local min at 160, and negative 5 over 2, negative 160 as a local max. But the maximum y value, not going to find it because there is no maximum y value. There's no minimum y value. Just one of the warnings about relying on computers, relying on algorithms to find answers. You will find an answer, and that answer can be nonsense. Anyway, we'll continue with some more interesting examples next.